Hello everyone, this is Dr. Rhonda Kofelt. Welcome back to part 3 of the aqueous ionic equilibrium or buffer chapter in the TRO book. In this part we're going to look at titrations and how titrations act as buffers as you're going through the different steps. Now that's going to be for our weak acids and base, but not for strong acids and strong bases. Strong acids, strong bases, you can use Henderson-Hasselbalch very easily, or the ice, either one. But it's, like I said before, it's pretty easy to go ahead and do the Henderson-Hasselbalch rather than going through the ice. The only exception to that is, of course, when you have the buffer, you've got to at least do that first ice table to get the new equilibrium concentrations using approximation. So a titration is where you're doing or performing an acid-base reaction, and you have a solution of unknown concentration, which we call the titrant, and we slowly add that to a solution of known concentration from a burette until the reaction completes. And so when it completes, we'd reach something called an equivalence point. And it's equivalent because your moles of H3O plus acid are equal to your moles of OH minus. So H3O plus is equal to OH minus concentration-wise. So the number of moles, okay? Now that's equivalence point. There's another thing called an endpoint. And an endpoint is where you see the change. And what we use to show us those are called indicators. Usually they're color indicators. And the color indicator changes color when the pH changes. And so it'll be one color at a low pH, and then at whatever the pH range is for that particular indicator, it will change to show you the pH. And it will change colors, and you say, oh, that's it. That's the end point, okay? The end point is where you see the color change. Now, that point is so close to the equivalence point that we use that as the estimation of the equivalence point. All right, and so we select these individual indicators so that their endpoint will be right there where we predict the equivalence point will be. So when you're doing a titration, you have, in this particular case, we've got an acid in our Erlenmeyer flask, and we are adding base to it. We know the concentration of the base. Okay, don't know the concentration of the acid in this particular point. We do know though how they normally react, and when we can tell by how many milliliters or moles that we add from the base, that'll tell us at equivalence how many moles of acid we have, which will then allow us to calculate what the molarity is. So we've added an indicator, okay, and the indicator is clear in a low pH and pink in a high pH. So when we reach that equivalence point, that is where we go from acid to base, it's going to change color, and we're going to be able to easily see that, and we'll stop our titration and check our volumes. So a titration curve is the plot of the pH versus the titrant. Okay, usually it's the volume in milliliters. And before the equivalence point in the flask is going to be in the acidic range. Okay, so like the pH, like you're going to have all acid in here right now. So as you're adding base to it, if you recall when we were looking at that earlier, when you add base to this, the base is being used up. So the base is used up, and so all you have in here is acid. So you just find the new equivalence point, and then, or the new equilibrium, and then you can figure out what those concentrations are. Then there is a almost straight line transition, And it will, in this area right here, the equivalence point is halfway up that straight line. And then when you get past that, everything in there is a base because all the acid's used up. So the equivalence point, if you have a strong acid, strong base, you're going to produce a neutral salt, okay? And that's going to give you an equivalence point of a pH of 7. If you have a strong acid and a weak base, the equivalence point is going to be less than 7. That is closer to the acid side. And then the converse of that is if the pH will be greater than 7 at equivalence if you have a strong base and a weak acid. Once you get beyond there, though, you see it changes to the other one, okay? And so that's why we go ahead and keep adding, even though we think we've seen the equivalence point sometimes, so that we can go ahead and draw that curve on out. If you do it with a pH meter, then you can take these readings and produce this curve, and it will look like that, and it makes it easy to calculate the exact equivalence point. So when you titrate a weak acid with a strong base, the initial pH is going to be of the acid. Typically, you're going to see on the graph that you're going to start higher than 2. That's most weak acids are going to have a pH that's higher than 2. Prior to the addition of the base, then it's a weak acid problem, just like we did before. So we work these as a weak acid problem. Before the equivalence, in this area, it becomes a buffer, and you work it as a buffer problem. And then finally, when you get past that equivalence point, it goes back to being a base problem. We've seen all of these, okay? We've seen how to do these if we just added a certain amount. Now what we're going to do is we're going to see what's actually happening while we're doing the titration itself, because that pH is going to change as we go. So when we reach the equivalence point, what that means is that moles of acid equal moles of base. Okay, moles of acid equal moles of base. And so we have established an equilibrium. And so in order to figure out how many moles we have to take the amount that we have divided by the liters. So like if you got it in molarity and it's moles over liters, okay, you would multiply that by liters to get the number of moles. That's going way back, if you remember, from Chem 111. Okay, because you're going to calculate that as a weak base equilibrium problem. Beyond the equivalence, then you're going to see that you have OH in excess, and it's going to be like a strong problem. All right, so I know, I can say it in words and all that. I don't know about you guys, but for me, it's a lot easier to actually visualize it when somebody works the problem for me. So in this particular one, what we're doing is we're adding volume, remember, and we know the molarity of one of them, and we know the volume. So what I'm going to do is it says that I am going to add 50 milliliters. So this is in A. 50 milliliters of a 0.2 moles per liter, right? Because that's what molarity stands for. All right, and this is my sodium hydroxide. They're both the same though. All right, then I got to get that liters to milliliters, so 1 liter over 1,000 milliliters. And that gives me 0.0100 moles of OH minus. And then the let's see. Then I've got nitric acid, 30 milliliters. Okay, so this is my OH, and this is my H plus. 30 milliliters times 0.2 moles per liter times 1 liter over 1,000 milliliters. And that's going to give me 0.0060 moles of HNO3, which is my acid. Okay, I'm just thinking of them in terms of acid or H3O plus, whichever one you want to do. All right, so that is telling me what I'm actually starting with. Okay, so it wants me to calculate the pH after I add 30 milliliters of nitric acid. All right, so I've got 0.01 moles to start with. I'm adding acid to it. Okay, so I'm going to use up 0.0060 moles. Remember, we're talking about moles this time. Okay, and then I'm going to, and so that's going to leave me 0.0040 moles of the hydroxide left, because that's the one I have more of, right? Because I have 0.01 moles of that, but only 0.0060. So that's the one I'm going to have left over, and I'm going to have used up my acid. Okay? So my hydroxide, all right, so that's the step one. Okay, and then for my hydroxide, then I'm going to add the 30 milliliters, right? So for hydroxide, I've got the OH minus equals the 0.0040 moles, right, divided by 0.05 liters plus 0.03 liters, okay, because I had, sorry about that, because I had 50 milliliters and 30 milliliters for my volume, and so my OH here is going to be in molarity is going to be 0.05 molar. Okay, let me go back through that. All right, so I had left over 0.004 moles of the hydroxide after I initially added 30 milliliters. Yes? All right, that 30 milliliters was 0.006 moles, so I took 0.006 moles away from my original 0.010 and had 0.004 moles of hydroxide left. So if I want to know how many that is, I've got to divide it by the total volume, which was 50 milliliters plus 30 milliliters, which is 0.05 molar hydroxide. So since I know the hydroxide concentration, I can calculate the pOH. It's going to be the negative log of that. And that's going to equal 1.30. Okay, but that's not the pH. All right, the pH then is going to be 14 minus that number, because I was using the base, so I was calculating the pOH. And that makes sense to me because that's a basic pH. This would not have made sense because that's acid and I've got a base in there. Okay, so you can kind of think like that. Okay, all right, now part B, it's asking me, what about at the equivalence point? All right, so what did we just say? What did we just say about equivalence point? We said the equivalence point is where the molarity of the H3O plus is equal to the hydroxide, right? And we said that at equivalence, a strong acid and a strong base is always going to be equal to 7. So you just need to know that. You don't have to work that. You just need to remember that when you titrate a strong acid and a strong base, your equivalence point is going to be 7, because that's when your H3O plus and your OH minus are going to be equal. Okay? Strong acid, strong base, always going to give you that. All right. Then what I'm going to have you do is go back to the original concentrations of 17.6, okay, the 50 milliliters and all of that, and then you're going to add 60 milliliters instead of the 30. So instead of 30 there, you're going to do 60 and see how that changes things. Okay? So that's your practice for this, but you're going to work it exactly the same. Figure out how many moles, see what you've got left, find the concentration of the H3O plus this time, okay? And then, because this time you're adding more of the acid than you are the base. So the acid is what you're going to have left over. Okay, so that's when we've just added some. All right, now, in this problem, what we're doing is we're taking it basically through part of a titration, okay, or through the equivalence point, okay? So again, you know some things about this, all right? So in the pKa for this, for HNO2 is 3.34. Okay, so the pKa for this is 3.34. All right, so that's a weak acid. And our reaction is OH minus plus HNO2. All right, and so this is strong, and this is weak, plus HNO2 is going to give us water, of course, and NO2 minus. All right, so that's what's going on with the reaction. All right, so the first thing it's asking you is how much does it take to reach the equivalence point? At equivalence point, the H3O plus is going to equal the OH minus. So we're going to figure out how many moles of HNO2 we have and how many moles of the KOH it would take to have that concentration, because they've got to be equal. So for the moles of NO2, I have 40 milliliters, okay, and 40 milliliters is equal to 0.04 liters, and 5 milliliters, well, we'll do that in a minute. But just remember, you divide by 1,000, okay? So I'm going to go ahead and do that up front. So I've got 0.04 liters times 0.1 moles of HNO2 per liter. And that gives me 4 times 10 to the minus 3 moles of HNO2. So that is the concentration, all right? So that's a concentration. That's how many moles I have, right? So then I can go to my KOH. So at equivalence, it also has to equal that. So I can figure out the volume by putting that I have 4 times 10 to the minus 3 moles of OH, okay, KOH in this case, times what? This time moles has got to be on the bottom, right? So it's going to be 0.2 moles per 1 liter, because that's the molarity. And that's going to give me 0.0200 liters of KOH, or 20 milliliters of KOH. So if you're looking at equivalents, then it just has to be equal to whatever the number of moles are of your known, in this case, acid. And then take those moles, plug them in, multiply by the molarity, because as long as you know the molarity, you can figure out the volume. Okay? Part B of that, the pH after adding 5 milliliters of KOH. So the KOH, and then this is the disappearing trick, right? So we have 4 times 10 to the minus 3 moles of HNO2 and 0 salt when we start. We're adding 5 milliliters of KOH to the mixture. So 5 milliliters of KOH times the molarity, which is 0.2 moles per liter, is going to give us 1, or I tell you what, or you can do it, this time I did it per 1,000 milliliters. You can do it either way, okay? 1 liter is the same as 1,000 milliliters, right? Right, just making the math simpler. And then you get 1 times 10 to the minus 3 moles of OH. All right, so I'm adding, so I did that because I need to look at it in terms of moles. I added 5 milliliters of KOH, and it's 0.2 molar. So how many moles was I adding? And I was adding 1 times 10 to the minus 3 moles. I use all that up because that's less than 4 times 10 to the minus 3 moles. And so I'm going to go down 1 times 10 to the minus 3 moles, which is going to leave me with 3 times 10 to the minus 3 moles of my acid. And I'm going to make 1 times 10 to the minus 3 moles of my salt. With me? So once I figured that out and I know what the new concentrations are, then I can do Henderson-Hasselbalch, okay? And so I can just plug in, because it's asking me for pHs, and Henderson-Hasselbalch is my pH thing that I always do. So plus the log of the salt over the base, right? And so we saw earlier that the pKa, it told us, I told you in the problem a minute ago, that it was 3.34. So I'm going to plug that in. The pKa is 3.34 plus the log of the salt divided by the base that I have left at the new equilibrium number. And so the pH is going to be equal to 3.34 plus a negative 0.48. If the number on the top is smaller, it's going to be a negative number, just so you know. All right, and so I'm going to take that away, and I'm going to get 2.86. 2.86. So that's what my pH is after I add 5 milliliters, or 1 times 10 to the minus 3 moles of hydroxide during my titration. Okay, now it's asking me What's the pH at 1/2 the equivalence point? 1/2 the equivalence point means that I have added half of the base of what the acid concentration is. If it was at equivalence point, they'd be the same, right? But 1/2 the equivalence point, I've added half. So I have added that, and again, 4 times 10 to the minus 3 is higher than 2 times 10 to the minus 3. So I'm going to use that up. And I'm going to go down 2 and up 2 moles. Okay. And so at 1/2 the equivalence point, I've got, they're going to be equal, right? So the pH is equal to pKa plus the log of the salt over the base. The pH is equal to, because remember I've got pKa's, okay? So that's why I can do it this way, even though it's a base problem. All right, and so pH equals 3.34 plus the log of 2 times 10 to the minus 3 divided by 2 times 10 to the minus 3, which is 1. Okay, and the log of 1 is 0. So the pH equals 3.34. So at 1/2 equivalence, the pH is the same as the pKa. All right, so at 1/2 the equivalence, I've added half the total amount of the acid from the base. Okay? And this one, your practice problem here, it wants you to calculate the equivalence point, okay? And so you've got to remember about equivalence point and what that does. You're going to need to use the KB in this one, okay? So if you need to figure out what that is, you already know the Ka and you remember how to get the KB. I already told you, if you recall. Okay, so go ahead and use that, because remember KW is equal to KB times Ka, right? So you've got, or sorry, when you're dividing, you're going to subtract. So you're going to be able to get the KB from the Ka by subtracting the KB from 14. All right. Anyway, that was just a heads up. And oh, and let me tell you, the correct pH that you're going to get should be 8.08. And remember, you're getting POH first, and then you're going to have to subtract 14 minus POH to get your pH. All right, so work on that one. It's a fun one, okay, because you're going to see zeros, and it's not going to make a lot of sense to you, and so it's kind of fun, okay? So you're going to have to, in the second step, you're going to have to use X's. All right, and that's it. Thanks for joining me.